Hello, this is the third and final part of Lecture 6b for ECE 361, Probability for Engineers, Fall 2016. In this third and final part of this lecture, we'll start on the material in section 3.5, Conditioning in Continuous Random Variables. We'll continue this section in the next lecture. So let's think back to the case of discrete random variables where we talked about conditioning a discrete random variable on an event, and we'll see that the notion here is very similar. All right, so we have an event A, and that event A has some positive probability of occurring. And then we're going to say that if I have a random variable x, and I tell you that A is true, then that's going to affect the distribution of x in general. If it doesn't, then we would say that x is independent of A, but in general we would think of x and A as being dependent. And if A is known to be true, then what is going to apply is what's called the conditional probability density function of x given A. And this is defined as the function f of x given A with the following property, that for any subset of the reals B, the probability that x is in B, given knowledge that the event A is true, can be computed by integrating over all possible values x in B of this function f of x given A. So, of course, this function, this conditional PDF, must be a valid PDF, it must be non-negative, and it must be normalized. Normalization in this context means if I set b equal to the entire real line, then I'm going to be integrating from negative infinity to positive infinity, and this conditional PDF must integrate to 1. If the event A, which is an arbitrary event here, is in fact the event that the random variable x takes value in some set C, then specializing this general definition to that case, I see that what I'm asking for is what is the probability that x is in some interval, say b, given knowledge that x is in some interval, say c. It might be intervals, might be a union of disjoint intervals, might be an arbitrary set. The definitions apply in all cases. But now I can use my basic definition of conditional probability. The probability that x is in B, given that x is in C, is going to equal the probability that x is in B and x is in C all over the probability that x is in C. That simply follows from our original definition of conditional probability as the ratio of the probability of the intersection over the probability of the conditioned event. And now what I can do is I can recognize that this is going to be the probability that x is in B and x is in C means that x is in the intersection of B and C. So that's why here I'm integrating over all x in the interval B and C. So in summary, the conditional PDF of the random variable x, given knowledge that x is in the set C, is going to equal the original unconditioned PDF divided by the probability that x is in C for any x that's in C or 0 else. Let's do an example to illustrate these types of computations. And this is an important example because it establishes a key property of the exponential distribution, namely memorylessness. And memorylessness is a surprising property, and we'll talk about what it means as we go through this example. So let's think of a light bulb. So I just changed the light bulb for a light socket, and that light bulb is going to last for some amount of time. So I turn on the light, I put in a new light bulb, I turn on the light, say it's in a closet, I close the door, and at some point that light bulb is going to die. And we're going to call the random variable t the total lifetime of that light bulb. Okay, and we're going to suppose that that random variable t, that total lifetime, is exponentially distributed with some parameter lambda. Okay, now at some particular time, little t, say 6 months after I've changed the light bulb, I open up the closet door and I see that the light is on. So what does that tell me? That gives me side information. It means that the total lifetime of my light bulb exceeds little t, in my example, 6 months. And so now the question is, given that you open up the closet and you saw that the light bulb had not yet died out as of time t, find the distribution for the additional lifetime, which I'm denoting by a random variable x, of the light bulb. So my figure here is meant to suggest what's going on. At time 0, we replace the bulb with a new bulb, and this duration here is a random duration, it's the total lifetime. This is some time t, and we suppose that when we observe the state of the light bulb at this time little t, we see that the light bulb has not yet died. Okay, so now given that knowledge, however long this light bulb is going to last, we can call x, this remaining time here, the remaining lifetime. So what I want to know is, what is the distribution on the remaining lifetime, given that I've observed the total lifetime to at least exceed little t. Okay, so here's my same figure. Now, our event A from the general discussion earlier, in this case, is going to be that the total lifetime exceeds the observation time, little t. And the question is, find the distribution on the remaining lifetime. And what does it mean to find the distribution? It means, given any candidate remaining lifetime, little x, I have to find the probability that the random remaining lifetime exceeds that candidate remaining lifetime, given knowledge that the total lifetime has exceeded the observation time, little t. So now I want you to recognize that the event that the random remaining lifetime exceeds the candidate lifetime, little x, is the same as the total random lifetime, t, exceeds little t plus x. And just look at the figure. If I say that my candidate remaining lifetime is, say, here, that means I'm looking for the probability that the remaining lifetime exceeds this amount. That's equivalent to saying that the total lifetime exceeds the known time, t, plus x, the candidate remaining lifetime. So if you think about that, you should see that that's true, that the event that the remaining lifetime exceeds the candidate lifetime, little x, is equivalent to the total lifetime exceeding t plus x. And of course, I can then substitute in the form of A, namely that the total lifetime exceeds little t. So then you see, I can now express my quantity of interest. What is the distribution on the remaining lifetime given my observation in terms of the random variable t? It's in particular the probability that the total lifetime exceeds t plus x, given that the total lifetime exceeds t. And now I use the definition of conditional probability. The probability of this given this is the probability of both over the conditioned event probability. In particular, I now have the probability that in the numerator, the probability that the total lifetime exceeds t plus x, and the total lifetime exceeds t, all over the probability that the total lifetime exceeds t. Now, the event that the total lifetime exceeds t plus x is necessarily a subset of the event that the total lifetime exceeds t. The event that you live to be 80 or more is a subset of the event that you live to be 60 or more. Okay? So their intersection is equal to the smaller event. If A and B are two sets with A a subset of B, then the intersection of A and B is A, is all I'm saying. So now my numerator is simply the probability that the unconditioned total lifetime exceeds t plus x. And the denominator is again the probability that the total lifetime exceeds t. And now I use the definition of the exponential distribution to evaluate both of these probabilities. And recall, I assumed that t was exponentially distributed with parameter lambda, which is to say that it has an exponentially small probability with parameter lambda evaluated at t plus x all over e to the minus lambda t. And now here's the key property. The multiplicative property of exponentiation tells us that this exponent in the numerator is equal to the product e to the minus lambda t times e to the minus lambda x, and therefore the two e to the minus lambda t's cancel, leaving only e to the minus lambda x. So e to the minus x is, of course, the probability that the remaining lifetime exceeds little x. So putting it together, we've shown the following crucial property, that the probability that the remaining lifetime exceeds x given that the total lifetime exceeds t, is equal to the unconditioned probability that the remaining lifetime exceeds x. In other words, the remaining lifetime is unaffected by knowing how old the light bulb already is. And if you think about it, this is a very surprising property that many other phenomena in nature do not have. If we were to say that the probability that your remaining lifetime is 20 or more years is independent of how old you are already, we would not have a notion of aging among humans, for example. So this is a condition. This is a special property that only is held by the exponential distribution, and it ends up being critical for much of the advanced math and stochastic processes and Markov chains in particular. So I hope you've learned a little bit about how you can apply this notion of conditioning a random variable on an event by considering this example of memorylessness. And this concludes part 3, the final part of lecture 6b of this video.